So with autoencoders, we saw a specific way of training these models to try to produce useful representations of our data. But now we're going to look at this problem a bit more abstractly and look at representation learning, which is precisely trying to get good representations of the data. So the motivation for this is that the way the data is represented, the features that we have, is very important to solve the problems in general. So consider, for example, the problem of computing multiplication or division by hand using Roman numerals instead of the Arabic numerals that we use. It would be much harder to do that because we don't have that neat decimal system that we can use for multiplication, sum, division, and so on. In machine learning, we also have this problem. If you have the right set of features, everything becomes easier. And we can even imagine deep learning as a stack of feature extractions, and then at the end, a very simple classifier or regression model or something like that, after the whole network transforms the data into the right feature. So the idea here of representation learning is to learn the best representation or the most useful representation for whatever purpose we have of the data, so that we have the data represented with the right features that we need. And if you are trying to use very powerful models, for example in supervised learning with limited data, then you have problems of overfitting. But if you have the right features, you don't need such powerful models anymore. You can just apply simple models to those features. Now, unsupervised, semi-supervised learning, and even supervised learning can help here, but the idea of representation learning is trying to find the best way of representing the data, the best features. Now, why and what would be a good representation, and why can we expect to find it? This is a useful paper if you want to take a look. I'm just going to give you some highlights. But these assumptions that we can make about the data lead us to conclude that it should be possible to find useful representations. So one of them is that the actual data is just a small subset, a manifold of all the possible combinations of the input values that you have. So imagine that you generate images by randomly assigning colors to all the pixels. It will be nearly impossible for you to have an image of something. You will not have an image of a dog or a bee or a mountain or something like that. You'll just have things that look like random noise and there's nothing there. So if you imagine the set of all possible photographs, they are a very small manifold inside the set of all possible RGB images that you can generate. So the idea here is that the actual data is distributed in this subspace, and if we can find that subspace, we can get a much better representation of the data. It's also usually the case that the different examples that we have different combinations of independent factors. So you can have cars in different colors, or you can have objects that are the same color, but one is a car, another is a boat, and so on. And the differences between them, these different aspects are independent. Also, these factors can be organized in hierarchical structures. You can have, for example, in images, this is easy to imagine, which is you have details like edges and colors, shapes and contrasts and so on. And these, when combined, can result in more complex shapes like circles and 8, 9, and these combined can result in more complex shapes like words or cars or dogs, something like that. So these factors that explain or that inform us about features usually have these relations. It's also the case generally that unlabeled data is much more common and much more abundant than labeled data. Labeling data takes some effort. It's much easier to find images of anything on the internet, but harder to have properly labeled images with the descriptions of everything that is there, for example. So if we can use these unlabeled data to learn the structure of the data, then we have a lot more information available. There are also shared factors, and we saw this last week, in which some problems depend on some kinds of features, and other different problems may depend on similar features or partially on the same features, so that you can, for example, train one network with fashion NIST and then use that one with small adjustments to solve the classification of the NIST dataset. These features also tend to be sparse. Generally, each example only contains a few of the factors. If you have images of animals, some images contain wings, some images contain legs, some images contain scales, but these features do not appear in all of the, not all of the features appear in most images. So these features tend to be sparse across the examples. And the function, whatever function that we're trying to learn that maps from the examples to whatever we're trying to predict, tends to be smooth in the sense that if inputs are very similar, then the output should be similar too. If you have an image of a dog and slightly change a pixel, you don't want that image to be classified as a horse or something like that. So basically, if we can capture these, and note that all of these attributes of the data set, or all of these aspects, should be present even in unlabeled data, so we don't need to specifically train something to solve our problem. But if we can capture this regularity, we can extract useful features from the data that then we can use to solve generally other problems. So these features can be used in different problems, and when we are doing supervised learning, we have the first layers of the network, or the hidden layers of the network, trying to find the appropriate features to solve the problem. But even in unsupervised learning, when we are just learning the structure of the data, we can also find these regularities and find these features. So the idea of representation learning here is to find ways, maybe supervised but often unsupervised, of finding these aspects of the set of data that we have, so that we can extract useful features to solve our problems. So one example of this use, it's no longer used this much, but it was the first method for training deep neural networks, and it illustrates this kind of potential, was this greedy layer-wise unsupervised pre-training. So before rectified linear units and good optimizers, there was this problem of training deep neural networks. For example, you have the vanishing gradients problem if you use sigmoid activations, and so it was not possible to train a deep neural network from start with backpropagation. But one way of solving that was to take the first layer of the network and train it as the encoding of an autoencoder. So you put the data in, you want the same data out, but now this layer is learning to create a representation of the data that captures its structure. And now you use the output of this layer as the input of the next, and you train the next one as an autoencoder too, to output the same as the first layer and to create this representation of that particular representation. And now you keep doing this, so for each layer you do this greedily, you try to optimize each layer individually. Usually these are done with noise, including noise to make the representations more robust, and then just stack everything, and the network is already pre-trained to learn representations that are useful, at least in the sense that they allow the input to be retrieved after these transformations. And then you can just fine-tune with backpropagation, but now it's just to not training from the start, just fine-tuning. And this was one way of training deep neural networks before rectified linear unit and the kind of hardware that we have. So this works basically because this initialization, this pre-training, has a regularizing effect, and not only it allows you solve the problem initially of the vanishing gradients that did not allow to train deep neural networks. But it also helps as a regularization because instead of starting at random, we are starting with a configuration that already is capturing some structure in the data. So this kind of approach, I'm going just to skip a bit here. This is an example of using this pre-training to illustrate this regularization effect. So these plots here represent sequences or trajectories of the weights of the networks during training. So networks were trained 50 times, and the representation here is how the weights evolved over different epochs. Of course, the network has millions of weights, so we need to reduce dimensionality to plot this, and this is with t-SNE, and this with ISOMAP. So if you recall, t-distributed stochastic neighbor embedding is very good for looking at local neighbors, but at long distances it doesn't care if it's very far away or just far away, because it's no longer a neighbor. So it changes the scale like that. ISOMAP traces through the graphs of nearest neighbors, so it preserves better these larger scale distances. But in any case, you can see that without pre-training, the networks all run through a different region than they do with pre-training. And if you look here at the ISOMAP projection, without pre-training they are much more scattered on the combinations of parameters, but with pre-training they focus a lot on the specific region. So this is an example of this regularization effect of pre-training, because instead of initializing at random, you're already focusing on some specific configurations. Learning good representations in general is very good when we have poor representations of our data. So this is an example of human actions data set which has 5,000 dimensions, because these are combinations of values in motion sensors that are attached to the persons. And so we have these huge vectors to see all the kinds of movements, but for any particular instance, only about 2% of them are not zero. All the rest are at zero. So this is a very poor representation of the data, because we have huge vectors mostly at zero with just some scattered ones over there, some scattered values there. Now, training a denoising autoencoder with regularization here, and then using PCA on the hidden layer. So this is a projection in 3 dimensions, but the autoencoder can have more than these dimensions. But here we already see in this representation 3 very well-defined clouds of different patterns in movement. So this is an example where extracting this representation, getting this representation, was of great benefit, because the original representation was particularly poor. So this also happens a lot in natural language processing, because if you want to describe a document, for example, the way of doing this is to create a vector for each word, where you indicate what the word is. And that is done by one-hot encoding, where you have, for example, if you have 10,000 possible words at each position, for each position of your document, you have a vector with indicated the first word is this one, with a vector with 10,000 zeros and only one, and then the second word is this one, and so on. So those kinds of representations are very, very sparse and very poor. You have a huge dimension with very small amount of information there. But if you can create good embeddings from this, capturing the pattern that you have in documents, because not all combinations of words appear at random, then you can have good representations of these words in more compact vectors. When data is scarce, you need regularization, and pre-training provides this regularization, as we saw in this example. And so this this kind of training that we can do before actually starting to solve our problem can help in these ways. So this unsupervised pre-training is not only important historically because it was this first practical method for training deep networks. Nowadays we don't use this method anymore of training layer by layer because it's not necessary with rectified linear units and the kind of hardware that we have. And it has this disadvantage in that you have different stages of pre-training and then fine-tuning and so on, and all of these have hyperparameters that you need to adjust. But there are many applications where having these so-called foundation models where you have something that is pre-trained to capture the structure of the data, and then you can use those representations in different problems, are very important in some fields. For example, in the natural language processing, you can train embeddings for particular languages by training networks that try to predict, for example, a missing word in a sentence. You give the network a sentence with one word missing, and the network has to predict what word is missing. And you do that works similarly. You can do that unsupervised because you just extract sentences at random from that language. But then this creates an embedding that you can use for supervised learning problems, for classifying documents, for recognizing sentences, things like that. So there are lots of applications, some applications where this pre-training is very important. And this is related also to transfer learning, which we saw last week, because now once you have this model and this good representation, you can apply it to new problems, either with very little training, because you just need to fine-tune part of the model, you use some part of the model and then fine-tune something, or even in this case of zero-shot learning, you can do that without any additional training. So this is one example from this paper, where we have an unsupervised learning stage that learns the embedding of words. So we have here a manifold representation of words that puts words that have semantic similarities close together and words that are very different or not usually used in combination are far apart. But the words are projected into this continuous hypersurface. And then we have a supervised stage where we use labeled images and map them, train a model to map them to the appropriate word in this space. So to the appropriate coordinate of the word in that space. So we can train that with car images, with horse images, with dog images and so on, all into the correct positions of this manifold that was learned and supervised. And now this is the transfer learning with zero-shot learning. We present an image of a cat, but we never trained anything here with cat. So cat was not one of the categories we're looking at. And now the network maps cat to a point in this manifold that is close to the word cat. So it actually can understand or identify that image as a cat without having been trained to identify that image.
How do we say what image is a word? How do we make that correlation?
Okay, so the first step was this unsupervised manifold learning of the word. So now each word is a vector, is a coordinate on this space, okay, a set of numbers. Then the second step was the supervised training of images to the vector of the word. So car images, the network outputs a vector corresponding to the car word.
But the cars are labeled.
The cars are labeled, yes. So this is supervised learning, horse and so on. But now we have the cat, and there was never an example of a cat, but the network that learned to map from images to the word manifold maps to a point in the manifold that corresponds to cat. So this would be an example of applying this to a new problem without even training for that. So here we can see these ideas of transfer learning and representation learning. They are not the same thing, but they end up being related in practice. Representation learning is a more general idea of trying to learn the good representations. It can be supervised or unsupervised. Often it is unsupervised in this using very huge data sets that are unlabeled, for example, in natural language processing. Transfer learning is specifically trying to use model or a part of a model that we obtained training with one particular problem and using that in a different problem. Of course, if we have good representations there, if we manage to have a good representation of the data, then transferring what we learned becomes easier because it's easier to generalize outside of the initial problem. So with supervised pre-training, we can also take advantage, in this case, of previously trained models. So this is a particular example that I mentioned last week, where you can use these models that were already trained and then apply them to your problem. You have there lots of applications, different image recognition networks that you can use in Capture. Okay, so now I'm going to talk a bit about the exercises for this week. One is to do that thing I showed with the banknotes. You can experiment with different architectures of the autoencoder, but the idea is to transform from 4 dimensions into 2 dimensions. So your autoencoder will have the input, which is a 4-dimensional vector for the banknotes. Then you can put any number of neurons that you want in the layers and try different layers, but the middle layer should have 2 neurons because you want to project things into 2 dimensions. And then you need to create a decoder, which is the mirror image of the encoder, so that it does the same thing as the encoder. This, strictly speaking, is not mandatory. You can create an encoder different from the decoder, but in that case, the encoding will not be exactly at the midpoint, and one of the parts may be doing more work than the other, and you may not have such a good encoding at the end. So this is the general approach: use a symmetrical autoencoder. Now, one thing that you need to do is you need to add 4 neurons at the end, because these will represent the input. These are the outputs that you are going to compare with the input. So in the case that you have unconstrained values, so they can be negative, positive, continuous, and so on, you should have just linear outputs there. If you have values that need to be constrained between 0 and 1, you can use sigmoids and you can use some activations there. But in this particular case, these 4 neurons should not have activation, because if you standardize everything, then you have some negative values, some positive values, and such. You can try different activations, different optimizers, and the idea is that you create this autoencoder, you create the encoder part and the decoder, so that then you can project your data into 2 dimensions. And then you can compare this with PCA. So basically, you train your autoencoder, then you create the model for the encoder. You can create it from the inputs into the encoded region, like you did last week for transfer learning. Or I can show you a different way of doing that in the next example. But the idea is to make this comparison with PCA and then look at the results. So this would be an example of plotting in 2 dimensions or transforming into 2 dimensions with the autoencoder and with PCA. Another example that you can do is to project the MNIST data set into 2 dimensions. So each image here is a 28 by 28 image, so it's 760 something values. But we want to project this in 2 dimensions, and this is an example of the result. You can see number 1 is here, then 0 is here, but 0 is somewhat overlapping. 0 is here, it's 9 and 4, they overlap quite a bit here. So some of the digits are harder to tell apart, others are very easy. But my autoencoder is not very good. You can experiment a bit better with yours. But the idea is to create your model by using the functional API. So you start with the input. You do, if you want, you can do batch normalization or not. Sometimes it's a bit risky to use this with the convolution layers, because some of these pixels are always at 0, and batch normalization will not work very well then, because they're all the same. But you can experiment with that, use or not. But the idea is that we reach a point here where we flatten everything and we have two neurons on a dense layer. And I did not put activations here so that I have any value can appear here. They are not constrained by any activation. So this is what will be the encoding. It will be two numbers corresponding to each image. And then we go back to the decoder, but this part called features is the end of the encoder. Okay? And we now keep stacking things for the decoder. Now there is, when you create these models, you need to do some calculations, because if I start with 28 by 28 and I do pooling and then I do pooling again, so if I do pooling the first time, it's 14 by 14. Assuming, I recommend that you always do the convolutions with padding, otherwise the calculations can become very complex. But let's assume that all convolutions have padding same, so that they don't change the size. And the only thing that changes the size is pooling. So when we have 28 by 28, we do pooling once, it's 14 by 14. If we do pooling twice somewhere here, we have a tensor that is 7 by 7, and with the depth of how many filters we are using here. So in this case, it's 7 by 7, the feature map, and we have 8 feature maps. So this is what is being flattened and fed into these two neurons. And now we need to recreate this 7 by 7 by 8 tensor before going into the decoder. So we can do that here by creating a layer of 8 times 7 times 7 neurons, and then reshaping this into the shape of the tensor. 7 by 7 of the tensor, the feature map, and then 8 layers, 8 channels here, because it corresponds to the 8 filters. So this 7 by 7 by 8 is the same kind of tensor that we have outputting here from this convolution. And now we go back, we do convolutions, we do upsamplings and so on, until we reach the final size of 28 by 28. And here I create a convolution with one filter only, because the images are 28 by 28 with only one channel. If we had 3 channels, for example, for color images, we would use 3 channels here. And I just added a sigmoid activation for convenience, because if you want to visualize the images or export them, the values should be between 0 and 1. Otherwise, if you try to save as a PNG or something like that, you can get an error. So I just put a sigmoid activation to make sure it's between 0 and 1, and I don't have to do any post-processing. But you can experiment with different things here. Okay, so now the autoencoder is the model that comes from the inputs all the way here to this last layer. So this is the full autoencoder from the beginning to the end, which is what we're going to train. And the encoder just comes from the inputs into the features layer. So it's only the first part. This one we cannot train because we don't know what the target is, but we train the autoencoder and then we use the encoder for prediction to create the representation. So this would be one suggestion, 32 filters, then pooling, then 32, then 16, then pooling, and so on. So the idea here is that when we do pooling, we are shrinking the tensor by 4 times, because we have a 2-dimensional feature map, and we divide by 2 on the width and by 2 on the height, so we have 4 times fewer values after pooling. So if you do pooling, you can either increase the number of filters so that you compensate. For example, if you pass from 32 filters pooling and then go to 64, you're actually only decreasing by half the total size of the tensor, because you cut down by 4, but then you increase the depth twice. Or you just keep the same there, so this step reduces by 4, and then this step reduces by 2-fold when you go from 32 to 16 with the same size. So that's why I used here the same number of filters when I do pooling, but then I reduce the filters by half when I don't do pooling, to try to make the encoder more smoother as it goes all the way down to 2 neurons here. But you can try with different combinations. And then it's important that the decoder does the same thing in reverse. So try to mirror the same operations to get back to the original image. Now, one important thing here is that if you recall from the classifiers on fashion NIST or NIST, with about 5 epochs you already had a good result. And once the loss function goes down and starts going down very slowly, with the classifier it's not a big advantage to keep training because it will not make much difference in the classification. However, with autoencoders, the devil is in the details because it's the first part of losing the loss function is just a rough approximation. But when the autoencoder tries to learn the details, that's when the encoding starts to become useful. So it takes a bit of time to train until you get a good representation, even if the loss function is shrinking very slowly. This is one way of checking then the representation. So I create the autoencoder and the encoder with that function, load the weights, and then use the predict on the encoder to create the two-dimensional representation. And then I plot the different categories like this. So save the weights for the autoencoder, but note that the encoder is just the first half of the autoencoder, so you can use that one for predicting. This would be to check the result of the autoencoder. So you load the weights of your autoencoder, you predict with the autoencoder the first 10 images on the test set, and now you get 10 images reconstructed that you can save with the image save from scikit-image, for example. So I'm saving the original and the restored image as PNG, and then I can compare. So this would be the original images, the restored images, and you can see that for the 4 and the 9, the restored image is very similar. So this autoencoder was still confusing a bit these digits, and that's why they end up being very superimposed here on the representation. Okay, so this is just basically a tutorial for you to follow all these steps, and it can help you if you have questions about the other simpler autoencoder. So to sum up, representation learning, the idea here is that we can, even with unlabeled data, try to understand how the data is structured and then create good representations there. And this is useful for transfer learning and for solving problems in general, because if we have good features, then everything becomes easier. I recommend that you take a look at this paper about representation learning. I gave you an overview of this, but there are more details there, and you also have this chapter here of the book.